Hello, Physics 20. So today we are doing universal gravitation, which is another of Newton's laws. So normally when we talk about this law, we are dealing with kind of space stuff and planets and things like that, but it can apply to other objects as well. So let's get into it. Consider when an object is held above Earth's surface and then dropped. It falls to the ground. Therefore, there must be a force that pulls the object to the ground, which we are familiar with and we have identified as the force of gravity. However, this is a new concept now. We say that the Earth must be exerting an attractive force on the object. So it's like Earth's core is attracting objects to Earth. Therefore, the objects will be attracted or being forced towards Earth. Namely, we think about this as falling. This attractive force is known as the force of gravity. So Newton's law of universal gravitation states that two masses will exert an attractive force on each other. The formula for this can be expressed as the following. Fg, which is our gravitational force, as I have down here, is the attractive force between the objects, which is force of gravity. Now let's just make a note about this, that we know this is defined as weight. Definition of weight. So this is still the definition of weight. We're just being more specific about exactly what is happening with gravity and what is this force. The big G there is Newton's gravitational constant. This is not something you have to memorize. Please take out your data sheets right now. So everyone take out their data sheet and go to the back of like your so you have your formula sheet, and then turn it onto the back where you see different things like it says here constants. So I want you to look at the place where it says constants. So it's on the top left-hand side. So we see A, acceleration due to gravity, 9.81. Okay, we're familiar with that. Then the next one right underneath, gravitational constant, big G, 6.67 times 10 to the power of negative 11. So this is the constant that Newton observed. And so, again, you don't have to memorize it. It stays the same. M1 and M2 are the masses of the two objects that we're looking at, and when we're looking at the attractive force between the two. Now next, there's a couple more constants that you need to be aware of. So when we look down, we've done acceleration due to gravity, gravitational constant. Next one is radius of Earth. Oh, I can't spell today. Radius of Earth, which it says is R subscript E, is equal to 6.37 times 10 to the power of 6 meters. So that's like the radius from the core. Okay, so if we were looking at spherical Earth, the radius is from the core to the surface. So that's what we're talking about there. And then the next one that you need to be familiar with is mass of Earth. So that's M subscript E, which is 5.97 times 10 to the power of 24 kilograms. So again, you don't have to memorize these, but you need to be able to know where to find them on your data booklet, so become familiar with that and make sure you have this with you when you're doing your questions. Now, to use the equation Fg equals mg, it can only be used if the acceleration due to gravity is already known for the one mass, so if it's on Earth. But as I said before, we are using this other formula to kind of, we're going to be comparing planets and things in space. So that's why we have this new formula, because we don't know the acceleration due to gravity, or there's lack thereof in space. Okay, so next, the gravitational force between two masses, if we're taking this formula, is directly proportional to the product of their masses. So when we look at our formula, Fg is equal to big G m1 m2 over r squared. We can say then that our Fg is directly proportional to m1 times m2. And when we think about directly proportional in an experimental sense, this means as the manipulated variable increases, so does the responding variable. So those two are directly proportional. So say we were to look at a graphical representation of that directly proportional relationship, we would look, let's do this graph here because it's right there. So we'll have our Fg on the side is in newtons, and this will be force versus mass. And I'll put my mass down here in kilograms. So if they're directly proportional, we would expect to see a relationship as this, where Fg is directly proportional to mass, which is similar to y is equal to x, and so we see that straight line. Now the next example, gravitational force between two masses varies inversely to the square of the distance between the centers of the mass. So now we're looking at distance. So if I looked at Fg is equal to G m1 m2 over r squared, I would say, so therefore, Fg is directly proportional to the inverse of r. So what this means is as the manipulated variable increases, the responding variable decreases. So what would that look like? Well, let's do a force versus distance graph. So we have force as our manipulated, or this would be our responding, and our mass would be our manipulated. Oops, I meant to put distance. Distance in meters. So if Fg is inversely proportional to 1 over r squared, then it would be like y is equal to 1 over x squared. I should have put a squared here, actually. Sorry about that. So our graph would look as so. Okay, so this is just our graphical representations of the formula. Next, what we're going to do is look at a video of Cavendish's experiment. So Cavendish, this was an experiment to validate Newton's law. So he measured the value of gravitational constant using a torsion balance. So Cavendish measured the angle of rotation to determine the force that caused the system to rotate. Knowing the mass of the objects, the distance, and the angle, Cavendish was able to calculate universal gravitational constant. So I'm going to show you a video that another teacher did on this. And if you're watching this at home, you should just maybe YouTube to 6B Cavendish experiment and watch it as a separate video so that you're not watching a video within a video. And if you're in class, you can either have the sub search that one on YouTube, or I'll just play it right now and you can watch it.